All right, well, let's continue chapter 6. We're going to take a look at the electronic structure of the atoms. And just a couple quick review things. We remember N represents the energy level or the principal quantum number. But as the energy of an electron increases, the electrons are farther away from the nucleus. So that attraction is weaker and the orbital energy is higher than that. Okay. And if I have more than two electrons, the repulsion between those two electrons or any other electrons is going to give us different energies, okay? Now, for the order of energies, S is the lowest energy, followed by P, followed by D, followed by F. But we have a basic principle. Electrons in atoms tend to fill low energy orbitals first. In other words, it establishes the lowest energy possible for that arrangement of electrons. Okay, when we take a look at the capacity for subshells, notice that each of these little blanks here represents a orbital in which the electrons can be placed, such as the 1s, the 2s, the 2p, and the number of little blanks that we have in here represent the number of orbitals. So for the 1s, we have only a spherical orbital. Same for the 2s, but for the 2p, remember we have that hourglass-shaped orbital that goes in the X, Y, and Z directions. Okay, so we're going to be able to see those additional energies, and the reason they're listed at the same level is because they have the same energy. The word for that is degenerate. And we'll take a look at these diagrams a little bit more as we go. So we need to introduce something called the electron configuration. The electron configuration consists of symbols that have three pieces of information. There's going to be an integer, which is the principal quantum number, then a letter that designates the orbital type, such as S, P, D, or F, and a superscript that designates the number of electrons in that particular subshell. Now, if it's in the P orbital, I have 3 degenerate orbitals. I can have up to 6 in there. Now, there's not 6 electrons in the same orbital, but there can be up to 6 electrons in the P orbital. Okay. Now, we're going to go ahead and take a look at what this means, okay? So take a look at something as simple as helium, okay? The doctor's favorite element, helium, right? Especially a podiatrist, okay? Now helium has 2 electrons, and both of those electrons are in the 1s. So we say the electron configuration for helium is 1s2. I can also write something that is called an orbital diagram, and sometimes we use boxes. A lot of textbooks like to use boxes. A lot of standardized tests use boxes, but sometimes we use blanks. And I have 2 electrons in the 1s. Now I'm going to represent those electrons with arrows. And because they have opposite spins, an up arrow is going to be a positive 1/2 spin, a down arrow a negative 1/2. So the 2 electrons in helium are listed as such. Okay. Now what's nice about this, and I'm even going to make one of these a different color. We talked about the quantum numbers before, okay? Whoops, not going to use that marker. Okay. And that one's purple, whether you can see the purple or not, okay? When I take a look at this, each electron is going to have its own set of 4 quantum numbers, N, L, M, L, and MS. Okay, so this comes fairly simply. Where do these numbers come from? How are they associated with these electrons? Well, N is the energy level. I can just look here and see that N is going to be a 1. Now I am doing the electrons for this electron right here. Sorry, the quantum numbers for this electron right here that I've written in black. Now L is an s orbital. Remember, that is 0. S equals 0. P equals 1. D equals 2. F equals 3, etc. Okay. Now ML. Now, since the values of ML are from negative L to L, my only possible value here is 0. And for MS, I either have a positive 1/2 for an upspin or a negative 1/2 for a downspin. In this case, it is a positive 1/2. Now, those are the quantum numbers for this electron. I can also give quantum numbers for this electron, which I'm going to do in purple here. Okay, it is also in the 1s. So the energy level is 1. My value of L is 1. It's still there. Now notice that 3 of these quantum numbers are the same, but the Pauli exclusion principle tells us they can't all 4 be the same. So the last number is actually a -1/2, consistent with our down spin. So I have 3 different ways that I can represent things. I can represent an electron configuration, I can give an orbital diagram, or I can give the 4 quantum numbers for each of the electrons. Now, when I start going to higher levels, such as lithium, okay, lithium has 3 electrons. Now, I still have these same 2 electrons in the 1s, but doing an orbital diagram, I now add the 2s sublevel. And I'm going to put my 3rd electron right there. I'll see if I have another color that functions here. And that is going to be blue. Okay. Now my electron configuration, I'm going to have to make this a little bit bigger here. My electron configuration, I have 3 total electrons. So I've got, in the 1s, I have 2 electrons. In the 2s, I have 1 electron. So it's 1s2, 2s1. Now for my quantum numbers, I have 1 electron that has 1, 0, 0, 1/2, another one that has 1, 0, 0, -1/2, and this one that's in blue is going to have a 2. It's still an s orbital. ML still has to be 2, and this is 1/2. Now I can continue writing the orbital diagram and adding electrons for larger and larger atoms. I can write a set of quantum numbers for every electron that's there. And if I fill from the bottom up, this is known as the Aufbau principle. I fill from the bottom up, that means I fill the lowest energy level first. This allows me to recognize the lowest energy state of the atom, which we know as a ground state. Okay? I could have something that is in an excited state. Let's say I had one of these electrons, instead of being there, was moved up to here. Now, this is not the lowest energy overall. This is now at a 2. This is not a ground state. I can have electrons at a lower energy state than this. So we're going to say that this is something known as an excited state. Okay, so very simple. Ground state, excited state, it works out pretty simply. Okay, now this is lithium. I'm going to go ahead and move ahead a little bit farther on the periodic table. And let's go over to the element oxygen. Okay, and now you're thinking, oh, that's a good idea. Oxygen, oh. Okay, now oxygen, as we know from our periodic table, has a total of 8 electrons. Okay, and if I do the electron configuration, that's 1s, but there's 2. I have the 2s orbital that's also filled, that has 2. And I have the 2p. Now the 2p orbital is not filled. And this gives me 2p4. If I add the superscripts, this tells me the total number of electrons. This gives me 8 electrons, consistent with oxygen in its atomic state, 8 electrons. It is in the ground state, it's its lowest energy. So I'm going to show the orbital diagram for this. And the orbital diagram generally is shown as in order of increasing energies. Now, we actually can get these energies by measuring them by a method called photoelectron spectroscopy. I'm not going to show you photoelectron spectroscopy, but we are going to use energy levels that are relatively close to that. I could get out a ruler and I could get out my energies and I could draw exactly what they are. But what I'm interested in you being able to do is to show the relative energies. Now, the lowest energy is going to be the 1s, so I'm going to draw it low down on my diagram. Then I'm going to go to the 2s, and then the 2p is going to be slightly higher in energy. Okay, I'm going to try to do a little bit more symmetry here. And usually, we're going to put our numbers to the left of it. Okay. Now I've got 8 electrons to fill. If I fill from the lowest energy level first, I go here and here, and here and here. Now I've got 4 filled. In order to continue filling, I need to add one more thing. Now there is something called Hund's rule. That's an N. And this is very simply, I put one electron in every orbital if they're degenerate before I have a pair of electrons. And the reason is because I have two electrons, they are both still negatively charged. And those negatively charged electrons are going to repel each other. So even though they can be in the same orbital, because I have opposite spins, I'm not going to have them in the same orbital if there's another orbital of the same energy available. Now notice I've only put 2 of my 4 p electrons in there. My third one, again, is going to be placed here. And finally, with the fourth one, I place it there. Now, if I wanted to, I could draw or write out the quantum numbers for every one of these, N, L, M, L, and M, S, okay? But instead of doing it for everyone, I'm going to pick one of the electrons here. And I'm going to pick this electron right there. Now, that electron, what is N value here? Well, I find it right here, 2. L, it is a p orbital, so that's equal to 1. Now, how do I get ML? Well, if it was an s orbital, it's easy. There's only negative L to L. That's negative 0 to 0. There's only one possibility of 0. For the p orbitals, we're going to arbitrarily label these from negative 1 to 1, or negative value of L to L. And I'm going to say this one is arbitrarily in the negative 1. So that's a negative 1. And it is a down arrow, so it is a negative 1/2. So I have a set of quantum numbers. Now, since I have 8 electrons, I should have 8 quantum numbers total. Okay, and we would continue on this. Now, with the orbital diagrams, there's kind of a shortcut that we can also take, especially when we get into some of the larger atoms. So, for example, let's take a look at chlorine. Okay, now if I write out the electron configuration for chlorine, I am going to have Cl, and notice that chlorine, if I get my handy dandy periodic table, I have a periodic table. It's off camera here, but I thought I would show you here. Here's my handy periodic table. I don't have it up on the wall at the moment, although I will later. But if we take a look, we will see that chlorine right down here, helps if I do it on the right side, right down here has 17 electrons. So the atomic number that we see there is easy enough to see. And since it's a neutral atom, the atomic number equals the number of electrons. So to get to 17 electrons, I need to start out with the 1s, and I'm going to have 2 electrons there. The 2s is going to have 2 electrons. And your book kind of goes through a little diagonal filling diagram that we can go through. I prefer to just know what order the increasing energy is. 2p, which is going to have 6, and we're going to have 3s, which is going to have 2. Again, 2 and 4 are, so 2 and 2 is 4, and 6 are 10, 11, 12. I need 17. There's 5 more, so that's going to be in the 3p. 5. Now, if I take a look at this one right here, this is the same as neon, and I can represent this as any. Anyone have a problem with that? Okay. So I can write this as neon 3s2 3p5. And often when we do orbital diagrams, we only do the things that are higher in energy than our noble gas. Okay, so in this case, I would just have the 3s and the 3p. Okay, got a little careless in writing there. I'll make it a little bit better here. So I've got my 3 orbitals, which are all degenerate. Up arrow, up arrow, up arrow. Again, because of Hund's rule, 1 in each before we pair up. Down arrow and down arrow. And again, for any of these, I could choose to determine my 4 quantum numbers. So just for a little bit more practice, let's do this one. All right. And again, I could do any of the 17 electrons there. I chose just to do this one. For this one, N is equal to 3 right there. It's in the 3rd energy level. L, it's in a p orbital, so it's 1. ML, negative 1, 0, and 1. It is a 1st orbital, and MS is a 1/2 because it is an up arrow. Now, something happens when we get to argon, okay? And I know you're thinking, argon, oh, that's when it's not there anymore. That's not what I mean by argon. The element argon, Ar, has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Now, notice that the 3p shell, 3p6 is filled, okay? Now, this is argon. And if I want to go to the element that is higher in energy than argon, I'm going to go to potassium. Potassium has 19 electrons. And if I do this, 1s2, 2s2, 2p6, 3s2, 3p6, and you would think that the next thing we put in is the 3d. However, the 4s is lower in energy than the 3d. So I'm going to start filling the 4s, and this is for potassium, okay? I fill the 4s before I finish filling the 3d. Now, what's interesting about this is here I have 8 electrons in the outer shell. So what is the outer shell? The one with the highest value of N. Now, the third energy level, I can have 2 in the S, 6 in the P. I can actually have 10 in the D orbitals. That's 18. I can fit 18 electrons in the third energy level. However, you've always heard about this octet rule. Where does that come from? Well, if I look here, I now have 8 electrons in the outer shell. When I get more than 8 electrons, my outer shell now has 1. Okay? And I can represent this, instead of writing all of this, I can just say argon. And I know you think, oh, that's that argon. No, it's still there. It's still there. 4s1. Okay? Now, when I get to something like scandium, okay, I am going to actually fill this, and I'm going to get argon 4s2, 3b1. Okay. We can continue this way. Now, likewise, when I get to the f orbitals, I don't start getting electrons in the f orbitals until I am in the 6th period. Okay. So, whereas the d is 1 behind, the f orbitals are 2 behind. And we can take a look at those energies. So hopefully this will help you see this a little bit. Let's go back to our PowerPoint here. Maybe. Okay. And as I take a look at this, we now have an idea of how to put together an electron configuration, an orbital diagram, and getting the quantum numbers for each of those electrons. Okay. Just a reminder, the Aufbau principle, from Aufbau to build up. That means we fill from the lowest energy level first. We also have the Pauli exclusion principle. And here's the diagram that I was referring to, which has a diagonal rule. I fill the 1s, then the 2s, 2p and 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, etc. So this may be useful for some of you in order to be able to remember that. Okay. Another way to do this is to take a look at the periodic table. Now, if the periodic table, it counts along, and we can see right here that as I count, I've got 1, 2, okay, 3, 4, 5, 6, 7, 8, 9, 10, 11. They count along. Now, this group here is known as the S block. This group here is the P block. Then I have the D block and the F block. Hopefully you can see why they are called that, because this is where the last electron we place in the orbital diagram is going to be found in that particular orbital. Okay, so again, the orbital diagrams are sometimes represented with a box and not just a single dash that I was showing on the board. Here's a couple orbital diagrams that we might see. Going through a little bit higher in energy. Now, again, Hund's rule, I wanted you to see it written out. The lowest energy configuration shows if there are 2 degenerate electrons, 1 in each, before we pair up. Now, notice that this particular orbital diagram is just really simple. It shows everything is degenerate. 1s and 2s are not at the same energy. They're expecting you to remember that. I prefer the orbital diagrams that show an order of increasing energy, but we can still use these and we'll still see these, especially because in books, it's easy to put all the boxes in a row instead of putting them in order of increasing energy. Okay, we can see some more electron configurations. And I mentioned the noble gas configuration. So here we have the core electrons and the noble gas. Anyone have a problem with that? Okay. You didn't laugh at it the first time I said that either, did you? All right. So what this shows is that I can write it a lot simpler. I can tell where in the periodic table I start by looking at that noble gas. Okay. All right. D subshells can hold 10 electrons. F subshells can hold 14, and that's something that's going to be important for us. Now, there's some exceptions to the order filling subshells. Copper and chromium are not the only exceptions. They're the ones that you need to know. Okay, we expect copper to be 4s2 3d9, but instead it is not 4s2 3d9. Okay, let's stop sharing this and let's take a look at what happens with copper. In the case of copper, if I show 4s1 3d9 and I show the degenerate orbitals, I actually have the 4s and the 3d are degenerate. Okay. Now, if I was a good artist, these would all be exactly the same energy. And I would expect to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, because I have 11 electrons after argon. Okay. But what happens is that since this is degenerate and it is closer to the nucleus, this electron here actually comes down here, giving me 4s1 3d10 for copper. Now, likewise, chromium is going to be 4s1 3d5. There are others that do that. As a matter of fact, palladium in its ground state, both of the 5s electrons drop down to the d sublevel. Okay, so let's go back to our slideshow. Okay, and again, if you see a list of them, you'll find out there's a lot of exceptions as you get farther down in the periodic table. You are just expected to be able to determine our expected ground state completion for it, with the exception of copper and chromium. I want you to know those specific exceptions and that other exceptions exist. Okay. Now, phosphorus, here we see phosphorus. Now compare that to the diagram with the 1s at the bottom, then 2s, 2p, 3s, 3p. So you get the idea. Okay. 1s here, 2s, 3s, oh, sorry, 2p, 3s, 3p. So we can show this in order of increasing energy, or we can just show it here. You're expected to know that this diagram that we see here at the top represents the order of increasing energy. Okay. So the periodic table is not quite nicely arranged. The elements in the same group have similar valence electron configurations. For example, everything in the very first group has one electron in its s orbital, and that's it. So hydrogen is just 1s1, lithium 1s2, 2s1. And you can see how that would go. Okay. Main group elements are those that have the s or the p, and the valence electron for main group elements are those with the highest level of N. Now, sometimes you're going to see this written. So gallium has argon 4s2, 3d10, 4p1. If I look here, the 4s and the 4p both have N equals 4. Even though there's 3d electrons there, those are not the outer electrons. They're not valence electrons. So if I count the electrons that have n equals 4, I found that there are 3 valence electrons. And later on, we'll find out that I can represent those with dots, and I can show 3 electrons around gallium. We'll look at that a little bit later. Okay. Now, transition elements, we took a look at those. Another example is vanadium, 4s2 3d3, where I end in the d orbital. Okay. Now, please note, when I do the orbital diagram, even using the box diagram, if I show the d shell, I have to show all 5 orbitals, even if there's only 1 electron in there. We can also get to the the F electrons. Okay. Now, we can also represent ions. Now, everything I've shown you so far is showing the atoms that have the same amount of electrons and protons. But what about a cation, okay, which is a positively charged ion? Now, remember that happens when an when an atom loses an electron, okay? So if the atom loses an electron, I am going to have now more protons than electrons. But what we're going to see on the electron configuration, if we go ahead and look at the one that I wrote on the board here, stop sharing, okay. If I look at this one, copper can easily lose this electron here. And if it loses the electron here, we're just going to have argon 3d10. This is no longer copper, but the copper 1 plus, or copper plus. If I lose 2 electrons, it's going to lose one of these inner electrons here, and this is going to represent copper 2 plus. Now, generally, a lot of the atoms form more stable ions if they have the electrons ending up in a noble gas notation. Not all ions end that way, but a lot of stable ions do. And our most stable ions have the same electron configuration as a noble gas. An anion, we add an electron, okay? So one of the things that we can look at is in the case of sodium, we're going to have argon. See if I can get my thing to work here. Argon, this is for sodium, 4s1. For the sodium plus, it's just going to be argon. Okay. Now I can also look at another substance that is very similar to it, and that is that of chlorine. And notice that chlorine has 17 electrons. So chlorine is actually going to be neon. Ooh, drawing like crazy. Neon 3s2 3p5. But if I add an electron to it, okay, I am going to now have chlorine, which is going to have neon 3s2 3p6, which is the same as argon. Both the sodium ion and the chloride ion have the same electron configuration. We say these are isoelectronic. Okay, sorry about that mark there. And I could determine the electron configuration of each of these. That might be a good time for you to stop and practice doing each of these. Okay. Here are the answers to those. I'm not going to spend time on it. You can pause the video and look at it. Okay. And we will continue on in the next video with periodic variations in element properties.